Yes. All right. Hello, everybody. It is 2 o'clock, so I will start teaching. I think I might have a lot of content to get through today, so I'll try to make it all clear and not go too fast, but we will start right away. So welcome to week 5 of QDA. And as always, please feel free to put your questions and comments into the chat as we go. Paula and Yunhan will be around to answer questions as always, and I am always happy to pause and get distracted by things in chat and interrupt myself. So I also want to say, for the benefit of the teaching team, to the extent possible, if you have questions and comments, put them in the general chat rather than direct messaging them to one of us or another. That way we can kind of share the workload between us and like not have to repeat the same answers again and again. And by DMing a question to just one of us, it means that like now that person not only has the shared responsibility of the general chat and whatever else is going on, but they now also have this like second personal responsibility. So it's easiest for us if you put things in general chat, but if you have something that you're not really comfortable sharing with everyone, or a question that you don't want to share with everyone, you can also email us outside of Zoom, but that'll make things a lot easier for us to actually address every question. I also want to mention that next week's class will be a Q&A about the first assignment. The first assignment is, of course, due on November 4th, so 3 weeks from tomorrow. And yeah, for next class, instead of covering any specific statistical test, I'll be running a Q&A session about the assignment and sharing an example of a first assignment from a previous year. It was on a different topic than what your assignment is about, but you'll see some similarities. And I'll go over strengths and weaknesses of that paper so you have an idea of what we're looking for when we grade. I'll also have, so I've posted on Brightspace that assignment grading checklist. We have that like open while we read your assignment. So I'll kind of go through that with the checklist at my hand so you can see how I go about grading. For the second half of the class, I'll be taking open questions about R, any issues you might have encountered or things that you want me to go over again. So if you have any specific R questions that you want me to make sure I cover, please make sure you email me ahead of class. I like to prep my lectures as early in the week as possible. So the earlier you send me a specific question, the greater of a chance it will be to appear in my slides or in my R code. And please send specific questions. So like if you send a broad question, like, what am I supposed to do for the assignment? That's probably too general for us to give you very good feedback with. Especially because a lot of the assignment is about figuring out what you're supposed to do. Likewise, questions about which statistical technique you're supposed to be using, we can't answer that, as picking the statistical test that you're using is a big part of the assignment. And finally, I need to say this every year, but especially this year, because there are over 160 of you, we can't really give you feedback on a draft before submission. It would just be impossible for us to grade. It's already going to be impossible for us to try to grade all of these essays in a quick turnaround, but we're going to have to do that. But we can't also be doing drafts before submission. So if you have specific questions, you can ask us those, but you can't give us a draft and say, hey, read this whole thing and tell me if it's any good. So yeah, any specific questions you want covered, please just email to me after class today or tomorrow, but as soon as possible so I can prepare some content to talk about them. All right, that is my rant about the assignment and future stuff, but that's looking forward. Let's talk about this week. This week, we are in week 5, our second inferential statistical test. And that test is simple linear regression. Regression is going to feel somewhat similar to correlation, as it's about relating variables to one another in a linear way, but it goes a step further than correlation. It doesn't just indicate whether the variables have a relationship, but it also tells us how well one variable can be used to make predictions about the other variable. And when I say simple linear regression in parentheses, I'm not just saying that, this stuff's easy. This just refers to the fact that we have a flavor of regression called simple regression, which is when we have just 2 variables. And I'll reiterate that again, but simple linear regression just means we have 1 predictor variable and 1 outcome variable. So last week, I had the example of a potential research question we might have around correlation. This week, I will have a similar research question, sample question that we might have that we would use a simple linear regression to test. In fact, we're actually going to use the same example data set and same example observations from last week. We can think about this as an alternative question that we might ask from the same observations. Or it might be a next step question that we might ask right after we finish the previous study, right after we did our correlation study. So last week, we identified that there are these variables, that there's social media posting anxiety, the worry that someone might have about whether or not to post something on social media, and the variable how many tweets or how many posts on social media someone makes, how many tweets they make. And last week, we identified that those variables are related to one another in a linear way. Remember, we said that when we're using correlation, we expect the words relate or relationship or covary or yeah, pretty much those words are our big tip off that we should use a correlation test. If your hypothesis is asking you about a relationship between variables, you're doing a correlation. This week, I have a different research question. This week, instead of asking about a relationship, I want to ask if you only knew one of those variables, if you only had one piece of information. So let's say you only knew someone's anxiety level, their social media posting anxiety level. Can you use that to make a prediction about the amount that they tweet? How good would that prediction be as compared to whatever prediction you would make without that information, without their social media posting anxiety information? And our keyword this week is predict. And this is like my big like siren blinking lights. If you see the word predict, you're using a regression. If you don't see the word predict, if you're not making a prediction, you should probably not be using a regression model. I'll say that again. Our keyword that I have in bold and big letters is predict. If you're not trying to make a prediction, you're not using regression. If you need to make a prediction, if your research question, if your hypothesis is about a prediction, then you're using regression. Yeah, I don't know. I should have got like a siren light or like some air horns like wah, 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 prediction. And last week, wah, relationship. Yeah, so the word predict is our keyword here. This is how we know we are using regression. So let's formulate our hypotheses. So last week, we had a research hypothesis that we said was testable, specific, parsimonious, falsifiable. It was a version of that question stated as a statement that met those criteria. In this case, our research hypothesis is that social media posting anxiety significantly predicts the amount of tweets someone will make. Therefore, our null hypothesis is the opposite of that social media posting anxiety does not predict the amount of tweets someone makes. Again, our hypothesis is about prediction, and our hypothesis should be what we are seeking. Our hypothesis that we are seeking to falsify, our null hypothesis, is claiming that we cannot use one of these variables to make a prediction about the other, that our best guess about the amount someone tweets is not improved by knowing their anxiety score. And why might we have a hypothesis about prediction? So maybe you are collecting people's anxiety scores for some other study that you don't have access to their social media. Maybe they're completely anonymized and you have this list of anxiety scores, but you want to know something about how much these people post on social media. If you can use what you already have, if you can use social media anxiety score to make a prediction about some variable that you don't have, then you don't need to go collect that other data because you already have something that makes a prediction about it. If on the other hand, this variable that you already have does not predict that other variable that you're interested in, then you know you're going to need to go out and collect something else. You're going to need to either collect that variable or collect some variable that does predict it. So that's why we might want to use a hypothesis about prediction. That's why we might want to use a regression. Let's talk a little bit about what exactly a regression is. So a regression is a statistical technique in which you use one or more predictor variable to predict the value of some outcome variable. And the predictor variable can be continuous or it can be categorical. So you can have a number or a category, and that can be used to predict a variable that is continuous or categorical. If you have just one predictor variable, then you're using what's called a simple regression. And that's what we're covering this week, just using one predictor to predict some outcome variable. You could also instead have lots of predictors, have more than one predictor that all go into making a prediction about a single outcome variable. And that's multiple regression. And that's what we'll be covering in 2 weeks from now. Your outcome variable can also be continuous or it can be categorical. When we have a continuous outcome variable, that is, we're trying to predict a number, then we're using what's called linear regression, that we're using a straight line equation. If we're instead if we're trying to predict a categorical variable, we're trying to predict what category someone falls in based on some predictor variables. That's called a logistic regression. And we don't cover that in this class, but you can read about it in the textbook, and you very well may run into logistic regressions in papers that you read. For logistic regression, you might see the word classify. So that's your other like siren, classify if you're doing a logistic regression, if you're trying to predict what category someone falls into. But that's not something we cover in this class, so it's okay to not know about logistic regressions even after you've completed this module, QDA. For those of you with backgrounds or interest in machine learning, regression is the statistical concept that underlies pretty much every single approach to machine learning. Having an understanding of regression and maybe a little understanding of linear algebra is pretty much all of the mathematical tools that I'd say you really need to completely understand machine learning from the ground up. Some snarky data scientists like myself would, depending on the day, argue that machine learning is basically just a process of running lots and lots of regressions. And I put a snarky little comic here that if you're a machine learning expert, you might say, actually, the big difference between doing machine learning and doing regressions is I get paid to do machine learning, and you have to teach classes about regression to make money. Yeah, that's true too. Machine learning is a better paid version of just running regression. So let's talk about straight lines. So I said that regression is fitting a straight line equation, but let's remember what a straight line equation is like. Depending on where or when you learned algebra, you might have seen the equation written as either y equals mx plus b or y equals mx plus c. I think the Americans call the constant b, the Europeans call the constant c. It doesn't really matter. It's an equation for a straight line is just y, the y coordinate, the up or down, is related to the x coordinate, the left or right, by m, the slope of the line. And then b, or c, is the constant. That's how far up or down on the y-axis the line crosses that y-axis. For linear regression, we use a very simple formula, very similar formula. Very simple, maybe, that's up to you. Very similar, yes. We use a very similar formula. We talk about specific points on our data set, some of which will fall right on our regression line, as you see with like some of these points like here, maybe some of these, and some will not fall on that regression line. For a given point, for a given participant, we can say that their value for the outcome variable, y, is can be expressed with an equation. Sorry, lost my part in my notes. I want to make sure I say this right. You can say that their outcome variable, y, is equal to the value for their predictor variable times a slope for that predictor variable, plus the y-intercept for the line, or minus. So yeah, the y-intercept can be positive or negative, and that just relates to the kind of scale of your variables. So if you have, let's say your predictor variable has like, or either of your variables has lots of negative numbers. So if you're predicting, I don't know how cold it will be in Antarctica based on the amount of precipitation. I don't know if those variables could possibly predict one another, but in that case, you'd probably see a really negative y-intercept because one of your variables is just on a negative scale. So the y-intercept doesn't have to be positive, but your straight line equation is that the outcome variable equals the predictor variable times some slope for that predictor variable, plus or minus the y-intercept, the constant. But since not all of these points fall on the line, there's plus one more thing, this epsilon, this residual. And that residual is how far above or below the line that given point fell. Each particular participant, each data point, not only has an x and a y value, but they also have a residual value. They have some value for how far away from the model equation that they fell. The betas, the slope, and the intercept of the line, these are a constant for our whole data set, that we have one slope that describes all of our participants, one y-intercept that describes all of our participants, and then each individual participant has an x and a y, so their actual predictor value, the prediction for their outcome variable, and the epsilon, the error, how far away they were from, how far away our prediction was from their actual y value. Since the equation can be expressed this way, I only need to know someone's predictor variable value to make a prediction about the outcome variable value. I can just use my intercept, my beta naught, and my slope, beta 1, to make that prediction. And then when I observe their actual outcome variable, I can see what my epsilon was. I can see what their residual was, how far away from their prediction they fell. And my cat decided that she would join for today's lecture. So say hi, Mutari. Are you helping teach? You're probably not going to be very helpful. All right. So let's see what our regression line looks like for our anxiety and social media posts data. So in this equation, this was generated a while ago. Posts is meant to be tweets, but our y-axis here is social media posts and tweets. Our x-axis here is participants. She's sitting right on my headphone wire. Our x-axis variable is the anxiety score that each participant had. So as you can see, the regression line is the line that describes this linear relationship that for some of our points fits really, really well, like points here and here and here. They're like right on that line. For other points, it fits really poorly, like up here or down here. These people have a really high residual for this regression line. So while this is the line that best describes our data, it might not be the line that, it might not be a great model for every single data point. So let's label some of our important points. So our intercept here is B naught, which is around 120, but this is not at 0. This is at like 15. So it might be that our y-intercept is something like 130 for this line. We can also try to figure out what our slope is, our beta 1, the gradient of this line. It looks like from as y changes from about 20 to 100, that's an 80-point change, and it looks like the corresponding change, that's a change in x is about 20 to 100, that's about an 80-point change from there. In y, that would be about 20 points, because this point looks like it's about 100, 100. This one looks like it's about 20, 120. So we would say that our slope is something like minus 20 over 60. So as we move down by 20, we move right by 60, or about minus 1/3, about minus 0.33. But we don't have to guess that. R will tell us what our equation for our line is. That's just me eyeballing what the equation for this line might be. It's something like y equals x times negative 0.33 plus 130, something like that anyway. But yeah, this is just algebra, basically. This is just rise over run. This is your slope of a line and your intercept for a line. This might be quite repetitive, especially if you found algebra easy, or if you have been using straight line equations a lot in your life. So how do we pick where to draw that straight line? That I potentially could have drawn a lot of different lines here. I could have drawn one up here. I could have drawn one down here. I could have put the slope more flat or more steep. How do I decide exactly which line to draw? That what line constitutes my line of best fit, my regression line? Do we just draw some line at random and hope for the best? Well, no, that would not be a very scientifically rigorous approach. Any line we draw is going to miss out on some of our data. Any line, any model is going to be wrong, but we want to minimize how wrong our model is. We want to minimize the residuals for the line. And we have a method for doing that, the method of least squares. The method of least squares is central to any statistical technique where we're assessing how well a model fits data. And again, we can think of this line, this equation, as a model for our data, as a way to make a prediction about our data, or a way to quickly understand the relationship between our variables. The method of least squares is how we fit a model so that it minimizes the amount of error, so that it minimizes the total residuals. And we'll go through the steps for the method of least squares to figure out what the fit of this model is. So we want to minimize our residuals. We want to minimize how far each point is above or below the line overall. And this is pretty similar to when we wanted to calculate variance, when we wanted to know how much above or below the mean each point was. So the mean was kind of our base model of a data set. Now we're using the regression line as maybe a slightly more advanced or an updated model. And again, we're going to figure out how far above or below this model each point is. Instead of using the mean, it's just the regression prediction line. Just like with variance, we're going to have some positive residuals, so some points that are above our prediction, and some negative residuals, some points that are below where we predicted. And we don't want them to cancel out, so we can't just add them together, or else, yeah, our positives and negatives would cancel out, and we would say, oh, my line is perfect. I found the line that perfectly describes this data. Instead, just like we did with variance, we square our residuals. That way, negatives and positives don't cancel out. They both become positive. Then we can add them all up, and we get the sum of squares. So we take the distance from the model, a data point to the model, distance from the data point to the model, take all of those distances, square all of those distances, and then add them all together. Again, just to look at our residuals, that's just the vertical distance, how far above or below our prediction line that our point was. So the difference is how many tweets more or less somebody actually made as compared to how much we would have predicted that they made. That's the residual that we're trying to minimize with this line. So are we just going to draw random lines? No, wait, what? So the line we're going to draw is the line that best fits the predictor in order to predict the outcome variable, that best uses the information of the predictor variable to fit the outcome variable. We don't want to just assume that our model is perfect, however. We don't, sorry, the cat was jumping off of my lap there. We don't want to assume that this is the perfect model. We need to make sure our model actually describes our data well, that just because this is the best line that relates these two variables, these variables just might not have much relationship at all, that the line that you can use to predict tweets using only anxiety might just not be a good model at all. So we want to compare our model to some other model. And the only other model we have when we're using simple linear regression is the mean. So we want to assess how much better our regression model was, how much better the line that we just drew was in making predictions about our outcome variable, about tweets, than just the mean is, than just using the mean for tweets. So if I had no information except I knew the mean number of tweets that people make just in general in the population, and somebody showed up to my office and said, how many tweets did I make? Then all I could possibly do, the only possible guess I could make is just guess the mean for every single person that walked in. If instead I also knew that anxiety can predict tweets, and for whatever reason I had a list of their anxiety scores, then maybe I could use their anxiety score to make a better prediction about their amount of tweets than the mean. But that's what we need to test. Is this prediction actually better than the mean? And how much better is it? So we'll start with the mean prediction. Again, the mean is a model of our data. So if I was only using the mean and I wanted to predict all of these people's number of tweets, I would just say for every single person, you made 100 tweets, you made 100 tweets, you made 100 tweets. That's the simplest model. For some participants, that's actually going to be a pretty good guess for people right along the line. But for a lot of others, it's a terrible guess. Now, what we're trying to figure out is our regression model, is the predictive line better than the mean at making that prediction? If I, instead of using the mean and just guessed 100 for everyone, if I instead used this regression line and guessed 121 for you, about 80 for you, 100 for you guys, would that be a better prediction than our mean alone? Yeah, so in this case, we're talking about predicting behavior, but we can be using, we don't necessarily have to be talking about predicting behavior. So like I said earlier, if our example was like predicting the weather using, predicting like tomorrow's temperature using today's like atmospheric pressure or something, that wouldn't be predicting behavior, but it would be using something we have access to, a measurement today, to predict some variable that we don't have access to, tomorrow's variable. And that's one example of why we might want to use a regression if we want to make a prediction about something that we either can't easily access or it's a pain to access or anything like that. So again, yeah, there's our mean, and we want to see how good or bad of a model our mean was. So we want to compare our models by using the method of least squares. We want to use total sum. First, we want to find this total sum of squares. So we want to find how good or bad of a model was first just the mean. This is total sum of squares. The amount of residuals, so the amount above and below the mean that each data point was. This is the same total sum of squares that we talked about for variance. We just add up the residuals, add up how far each point was from the mean, square them all up, add them together, and we have the total sum of squares. We have the sum of the squared distance each point was from the mean. So this is essentially our way of estimating how terrible of a model was the mean alone. So that's the thing we need to compare against. We now have an idea of how terrible was the mean. Then we're going to figure out how terrible is our model. Then we're going to compare them. And I got a DM that says, is there any method algorithm in R which predicts the regression line? Yes, I'm building up to it slowly, but R will give you all the information about your regression line. You don't ever have to calculate the sum of squares yourself. You don't have to do any of this like method of least squares of fitting lines and like trying to figure things out. But I teach all of this so you know what R is actually doing under the hood. In actuality, you'll run like 2 simple lines of code and it'll have your line for you. It'll tell you the equation of the line. It'll tell you how good or bad of a model it is. It'll tell you a p-value for how significant that prediction is. But before we leap right into that, before we just have R do it all for us, we're talking about what exactly R is doing when it does it for us. So yeah, total sum of squares. This is our measure of how bad of a model the mean is. Now let's figure out how bad or good of a model our regression line is. So we have a regression line and we also have these residuals and we get our residual sum of squares. This is the same operation. It's figuring out how far each point was from our regression line, taking that residual, squaring it, and then adding all of those squared residuals together. This is called your residual sum of squares. Again, we're squaring to make sure that negatives and positives don't cancel out. And now we're most of the way done, right? We have our measure of how terrible the mean was as a model, a measure of how terrible the regression line is as a model. Now we just need to make that comparison. We just need to figure out what the relationship between those measures of terribleness is. This is called our model sum of squares. And this is pretty simple. This is just, oh, you might hear my cat yelling, absolutely screaming because she hasn't eaten in a couple of hours. She'll be okay. Yeah, so next we figure out our model sum of squares. So we take our total sum of squares. That was our how bad the mean was as a model. We take our residual sum of squares, our measure of how bad the regression line was as a model, and we just subtract them. Simple enough. This is just asking the question, how much worse was the mean than our regression? What amount of residuals still remain even after we apply our new model? And this gives us our model sum of squares. And notice this number can only be positive or 0. This cannot be negative, because if our regression line wasn't giving us any information at all, if these variables couldn't be used to predict each other at all, then the regression line would have just been a straight line, and it would have been a horizontal line right at the exact same spot as the mean. So at very worst, if your regression has no information for you at all, it will just literally be the mean. So your the worst you can do for the difference between them is 0. You'll never have the case that your regression line was worse than the mean. You might have the case that the regression line was the mean, but never that it was worse than the mean. Someone asked if I could go show the residual sum of squares line. Yeah, this is just the squared residual, so the difference between the predicted value, so the point on the line, and the actual value. So this person's residual sum of squares, it looks like they're maybe at, I don't know, let's say 130, and their predicted value is like 118. So that's a positive residual of 12, square that, and it's a squared residual of 144. And you just get that square for every single person, add them all up. That's your residual sum of squares. Yeah, 0. So if your mean and your regression line are the same, if you have a flat regression line, 0 slope, that means your regression's terrible, that there's no difference between the two, and that your model sum of squares will be the same as your total sum of squares because your model isn't explaining any of that variance. So now we have a number that tells us how these different models, how different these models were, the regression model and the mean model. But that number alone doesn't really give us any context. So I just gave the example that like this individual participant's residual sum of squares might have been like 144. But you might notice that since our Twitter posts are on this scale, that could be, they could have made 1,000 Twitter posts, whatever, that because this variable has different dimensions, because the variable for this for this particular regression might be different than the variable for some other regression, it's hard to know just by looking at the model sum of squares how good or bad our model was, that this is going to be completely dependent on the scale or the unit we're using for our regression. So we don't just need to report the model sum of squares. We want to transform these so it's expressed in some way that anyone who hears a single number can know how good or bad our model was. So we want to scale this. We want to make it proportional. So instead, if we know the regression line is always going to be better, and why do we need to find the difference, if that makes sense? So the regression line can be a lot better. So in this case, it looks like it's pretty mildly better. But in other cases, it might be barely any better. Like it might be like 1% better, and it might be really, really hard to get your variable. So let's say I have all of these anxiety scores because I put out a survey. And let's say this survey cost me $100,000 per participant. And let's say that is 1% better at predicting tweets than just knowing the mean of tweets and using that as my prediction. While this model is literally better than my mean, I don't want to just rely on the regression, because the regression would say you need to go collect all these anxiety scores. You need to spend $100,000 per person just to get all of this data for 1% of improvement. That's probably not going to be, my boss, my funder is probably not going to like that. If my model, if I'm like, hey, the model was better than the mean, it was worthwhile, they'll say, yeah, you wasted tons and tons of money to get 1% improvement. And that's what we're going to talk about. That's why we get our sum of squares of the model. We want to talk about how much in a percentage we improved upon the mean. So we want to get a single number that explains that tells us how much variance from the model was explained by our regression line. We want to scale our model sum of squares in a way that it expresses the proportion of the variance that is explained by the regression line. So we just use a simple proportion here. We just divide that model sum of squares, that difference, by the total sum of squares, by the variance that the mean told us. And this gives us a proportion between 0 and 100, or between 0 and 1, of how good or how bad our model was, how much of a percentage of the total variance in our population that this model explained. And this number is known as R squared. R squared is called the coefficient of determination, which I think is the most metal name in statistics. I think that would make a tremendous name for a stats-themed rock band. The coefficient of determination is our measurement of how good or bad our model was, how much variance was explained by our model. When we report a regression, we don't just need to tell our reader what the slope and the intercept was. So we don't just tell them the equation of the line. We also want to tell them our R squared value, how much of the variance was explained by our model, how much better was our model at explaining variance than just the mean for the outcome variable. That is R squared. And this is, again, something that the program will just tell you. You don't need to do any math to get it. R just tells you your R squared value, which is kind of boring. But I wanted you to know how it all operates under the hood. So it's not just like, and then by magic, you get a value. That is what the value is telling you about. So we want to say whether or not the improvement over the mean, not just how big that value was, but we want to know if it was significant. And so great question. What is the ideal range for an R squared value? Well, it completely depends. But one possible way of seeing if your R squared was big enough is doing an F test, an F ratio test. And again, R will do this F ratio test for you. This gives you a p-value that tells you whether or not it was a significantly different model than the mean. That it tells you if the prediction that you got, if your R squared value was not only different than 0, but was significantly different than 0, given your sample size. So when we compare two models, we're going to compare the regression model to the mean model. And we're going to use a test called the F test. And R will automatically do this for you when you run a regression. You don't have to type anything in to do an F ratio test. But this lets us compare these two models and see if there's a statistically significant difference between the models. We work, of course, from the null hypothesis. The models will not be different. That our null hypothesis, again, was that anxiety cannot be used to predict number of tweets. And this null hypothesis is the same as saying that our our mean number of tweets will be, our regression number of tweets, our predicted number of tweets will be no better than our mean. That's expressing the same null hypothesis. And that's the null hypothesis that the F ratio test will be testing. So if our p-value is significant, if we have a p-value less than 0.05, then we can say that we did have a significant difference between our model and the mean, or in another way of saying that, we can say that our regression does significantly predict our outcome variable. So this works just like our other inferential statistical tests, that we get some size for an F ratio test, and then there's some known F ratio distribution for your sample size. And if there's a very big difference between the models, or if you have a very big sample size, then you might get a p-value below 0.05 that because you know how big your F ratio test is, you know how you calculate the difference between these models, and you know what the actual population distribution would be for an F ratio test with a null distribution. You can say how unlikely it was to observe an F ratio, how unlikely it was to observe a difference between the models as big as the one that you're observing for the sample size that you're observing. And that's how the p-value gets calculated. And if we have our p-value below 0.05, we can reject our null hypothesis. We can say that our model was statistically significantly better than the mean, or whatever other model we were comparing it against. And again, when you run a linear regression, R will just do this for you in the background and spit it all out in one line. Yeah, the p-value, again, is for a given statistic, for a given test statistic. This week, we're talking about the F ratio test. There's some known distribution for samples you might see given a null hypothesis. So your null hypothesis for the F ratio test is that two models are not different than one another. So you would expect a ratio of 0. You would expect that if you just sampled a bunch of points that had two models predicting them, and those models were not different at all, that the null hypothesis is true, this is the assumption we're making, then you would expect that the F ratio would be somewhere around 0. But depending on your sampling, you might get some that are a little bigger or a little different. But given your sample size, there's some known distribution. We know how many standard deviations. We know what the standard deviation is for each sample size. We can then say how many standard deviations away you were from the mean for that sampling distribution. In other words, you can say how unlikely it was to observe, or how likely it was to observe a difference that extreme. So for a very big difference between two models, for a lot of participants, it would be very unlikely to observe a really big difference between two models if the null hypothesis was true. It's less than 5% chance of observing this huge difference between these models if the true case is that these models aren't different. That means the difference that we observe, that really extreme difference, must have just been due to random sampling. But that's really unlikely if we have 100 participants, or if we have 200 participants, or whatever. This is what the p-value is calculating. How unlikely or how likely was it to observe a difference as extreme as what you observed if the null hypothesis is true? And this is all based on known distributions. So last week we talked about R, the correlation coefficient. That's a normal distribution. So we know how extreme we can expect values distributed in a normal distribution. This week, we're talking about the F distribution. So that has a different shape than the normal distribution, but it has a known shape. So we know if we see something this far from 0, we know how many standard deviations away that was. We know what percentage chance we would have observed that by chance. So that's what the p-value is telling us. How likely was it that we observed what we observed in a world where the null hypothesis was true? We observed this by chance. So it's not just our F ratio test that we want a p-value for. We want to make sure that each predictor variable is significantly different from the mean. In other words, we want to make sure that each slope is statistically significant from 0. Now, this week, it's simple linear regression, so you only have one slope. So if your F value, if your whole model is significant, then your one slope will also be significant. But in future weeks, you might have a model that's significant, but only some of your predictors are significant. And it might be that you're using 3 variables to predict one, and they do a great job of predicting that one because this one does all the work and these 2 are also there. In that case, you might have a case where your model is significant, but not all of your individual slopes are significant. So let's just talk about what it means for a slope to be significant. Our mean model assumes that the slope is a flat line. The slope is 0. There's no relationship between our predictor variable and our outcome variable. And to check that our slope is statistically significant from 0, we run a t-test. Again, R does this in the background for you every time you run a regression. A t-test is like an F-ratio test or a correlation coefficient test where there's some known distribution centered around 0 for our null hypothesis. And we can compare the difference between the slope we observed and 0. And the t-test tells us how likely would it be to observe a difference that large if the true difference was 0, and we sampled this many people from that population where the true difference was 0. This, once again, is what the p-value does. It's the likelihood we would observe something as extreme as we did given the null hypothesis. In other words, if there was no relationship at all between anxiety and tweets, this is how likely it would have been for us to take a random sample and find a slope this extreme. Once again, if we see a p-value smaller than 0.05, we can reject our null hypothesis. We can say that our slope was statistically significantly different from 0, that our predictor variable is significant in its ability to predict the outcome variable. Now, the moment you possibly have all been waiting for, what does a regression equation output look like? What does it look like when you run a regression in R? It looks like this. It gives you a lot of information. You get a very busy output. There's coefficients and intercepts and a slope and a p-value and another p-value and 2 R-squareds and an F statistic with another p-value. It's a lot to look at. Here is a labeled version that hopefully helps a little bit. We'll walk through each label here, and it will be hopefully a little less intimidating. So at the very top, this is the equation that you would run to get a correlation. You would run LM, and then within the parentheses, you don't even need to say formula equals. You can just say your variable that is your outcome variable, then the little tilde, the squiggly line, and then your predictor variable. And this is in the R file for today's class. So we see that our slope right here, for .data $anxiety, our slope for anxiety was different than 0. It was minus 5.6. And its p-value was less than 0. This is 1.38 e negative 9. That just means 1.38 times 10 to the negative 9th, or 0.0000000000138. That's all that means, but we would just say 3 stars. It is less than 0.001. So we would say our p-value is significant. Our slope was this, negative 5.60. And our intercept is this. Our intercept's always going to be significant. This is just a statement of fact of what the intercept was for this line. But our intercept was 555.26. Our slope was minus 5.6. So we could say as a straight line equation, our line is y equals x times negative 5.56 plus 555.26. So if we multiply our anxiety score by negative 0.56 and then add 555.26, then we get our number of tweets. E, that's just scientific notation. So E means times 10 to the blank power. So 1.38 E negative 9 means 10.38 times 10 to the negative 9th power, aka 0.000000138. But you can use the star codes to know your significance level. So 3 stars means less than 0.001. Yeah, so that's our straight line equation we get from these two coefficients. That's our intercept, that's our slope for anxiety, which we can see is significant. Next up, we have our R-squared value, and we see we have multiple R-squared and adjusted R-squared. Which one of these should you be using? You know, it doesn't really matter. What R does, so our actual R-squared value calculated with the formula that I just taught you, that proportion of your total model sum of squares to your total sum of squares, that exact value is 0.3136. R is going to adjust that a little bit. It's going to make that a little worse. R is going to instead say 0.3066. For the purpose of this class, we're going to use adjusted R-squared. What's happening is that R is probably noticing that our predictor variable is not normally distributed. So not perfectly normally distributed. So it's just bumping R-squared down a tiny bit to compensate for that. If you have multiple predictors, if you're using lots of different predictor variables, it'll bump your R squared value down a little bit more. So it's going to make a very conservative estimate for how much variance is being predicted by your model. But this R squared value is what percentage of your variance is predicted by the model. We would say 30.66% of the variance in tweets can be predicted by anxiety. Can you explain how this is significant? Could you rephrase your question? I'm not quite sure what you're asking. The 3 stars indicates the significance value. Yeah, so 3 stars just means that this p-value is less than 0.001. Or if you saw just the 1 star, that means it's significant. It's less than 0.005, but it's not less than any of these. Yeah, so that's your R squared value. That's the adjustment to the R squared value. We report this one, but the one that we just learned how to calculate is this one. But they're going to be really close anyway. As a quick aside, why would we penalize for having more than one predictor? Well, let's say we don't just want to use anxiety to predict tweets. We'll also use people's height and their weight and their browsing history and their blood type and what all their friends do for a living and what the last thing they bought at the grocery store was. There's a lot of reasons that a model like that's a bad idea. Now, big data people, if you're working for Facebook, you might say, well, that sounds like a great idea. Just sweep up all the data and we're good to go. For one, it's not ethical to collect more data than you need. That's invasive. It might only result in a tiny little extra bit of explanatory value, just a couple of points of R squared at the cost of maybe a lot of money and a lot of participants being very unhappy about all the data you were collecting. But for the real reason that R is punishing you is not an ethical reason. It's because complex models are worse than simple models. That the more different variables we introduce, the more likely it is that the data that we're describing only applies to our sample, that we're reflecting things just about the individual differences of our sample and not about the broader population anymore. This is the idea in machine learning of overfitting your model, that your model only now describes your particular sample, but if you tried to predict from other members of the population using your same model, you've made it increasingly complex. So that's why R bumps down R squared, why it adjusts it. That way it's being conservative, saying that, well, this is what R squared was for your exact sample, but we're saying for the entire population, it would be more like this. And R has some mathematical ways of doing that that I don't really know much about myself. Anyway, that was your little aside about R squared. Finally, let's talk about the F-test statistic. And this was just your way of determining whether this R squared is significant for your number of participants. So there's the F statistic, just like a correlation test. We get some coefficient for the F statistic, we get some degrees of freedom for the F statistic, and we get a p-value. I'll show you how to report it in just a minute, but first we'll just note that the p is very, very small. It's less than 0.001. So our model was significant, that our model was significantly different than our mean in being able to predict number of tweets. Now I'll let you in on a secret for simple linear regression. This p-value and this p-value, you might have already noticed, they're exactly the same. When we just have one predictor, as I already said, these two p-values will be the exact same. But when we have more predictors in our model, we'll have different p-values for each predictor that all come together to make the p-value for our model. But yeah, just note that since it's less than 0.001, we can say that our model was statistically significantly different than our mean, that we can say anxiety can significantly predict number of tweets. So this is a graph that you might have seen last week because I used it last week. Flashback. This was our correlation from last week. This was the correlation coefficient we got. We said R of 98 was minus 0.56. So that minus 0.56 was our R. Does anyone want to guess what would happen if we squared that minus 0.56? Yes, I'll get to degrees of freedom in just a second. If we squared minus 0.56, we would get 0.3136. For a simple linear regression, R squared is literally your correlation coefficient R squared. That doesn't work so easily when you have multiple regression, if you have multiple predictors. But in this case, simple linear regression, your correlation coefficient is exactly related to your coefficient of determination, your R squared. So 0.3136, our R squared and our correlation coefficient relate in that way. now you know how they are related, why we call it R and R squared, because they are actually, look, sometimes math's funny. I think this negative 0.56 might have actually been like negative 0.560431, whatever. It probably had some more decimal places after that got cut off. So when you square the actual full number that this would have been, you do get the actual full number of these. This is a statistical law. This is not just a random magic trick that I'm showing. So when we report a correlation, look at all these colors. I apologize if you are colorblind. I tried to put these in the order that they appear to the extent possible, but I have a lot of things that I need to label. So hopefully the labels make some sense to you, but I can walk you through if colors aren't your friends. When we report a regression, we need to report 3 things. So we want to report the equation of the line. So tweets equals minus 0.56 times anxiety plus the slope. Next, we also want to report the t-score, or the significance of our predictor. So if we go back here, our predictor, our anxiety coefficient had this value, this t-score value, and this p-value. They all hop right in here, and we had a number of degrees of freedom also. And then we have our R-squared value. We have our measure of how good the model was. We have a measure of, this is exactly what our equation was. This is how good our predictor variable was. And if we had more than one predictor variable, we would want to report each one of them. And then we have our total description of our model. So we have our R-squared value, our F-test score, and our F-test p-value. And our F-test score in parentheses has 2 degrees of freedom. First, it has your model degrees of freedom. So how many models were you comparing? -1. So 2 minus 1 is 1. We're comparing 2 models. Subtract 1, you get 1. And how many degrees of freedom were there among your participants? That is number of participants minus number of variables. We had 100 participants. We had 2 variables. So 100 minus 2 is 98. That's the same 98 we're using here. That's all of the numbers we need to report when we report a regression, but it looks super ugly like this, and this wouldn't be great to put into words. Instead, if I was reporting a regression for a report, for a paper that I was trying to publish, I would make it look more like this. I would say, our study found that participants' level of anxiety predicted their number of tweets over the past 6 months. Then I would report my R-squared value. I would report the F-test for that R-squared, and I would report the p-value. I would say the full model equation and betas are reported in table 1. And then over here in table 1, I would have my straight line equation. And then I would have, for each predictor variable, I'd have the name of the variable. So if I had more than one predictor, I would have them down here. I'd have the beta, so the actual slope for that variable. I'd have the t-score with the degrees of freedom. And I would have the p-value. And maybe I would reuse those star codes. So a reader or a reviewer could quickly be like, yep, that was significant. This makes it a little more easy to read by putting important stuff like this up in a table and putting the part that actually addresses your hypothesis right into the text. So my hypothesis, again, was that social media anxiety significantly predicts number of tweets. And the thing that actually answers that question is the R-squared of my model. So my R-squared and my F-test for the model, my R-squared was 0.31. My p-value for the F-test was less than 0.05. So I can say this supports hypothesis 1, that social media anxiety score significantly predicts number of tweets. I only put this part in text because this is the only part that's actually addressing my hypothesis. This stuff's important for someone to recreate my model, to recreate the line that I drew and to understand which parts of it were significant. But this is the actual answer to my hypothesis, that I can significantly predict number of tweets, that there is a significant difference between my model and the mean, and that this is how much variance that my model explains, 31% of it. So not great. Maybe I can add some more predictors and pick up some more variance, increase my R-squared, but it is statistically significantly predicting number of tweets. It's doing better than the mean at doing that. So that is simple linear regression. Well, what's the deal with simple linear regression? It's not simple. That's my 90s comedian impression for simple linear regression. Yeah, hopefully that was not too overwhelming. We went through a lot in not a lot of time. I strongly recommend you supplement this by reading chapter 7. You can pretty much just read the first 15 pages of chapter 7. That's page 245 to 260. That's simple linear regression. After that, the book gets into multiple regression. So we'll save the second half of that chapter for our next lecture. How do you measure anxiety by numbers? So in this example, the anxiety score was, we were saying we were measuring it with a questionnaire. So we were saying we'll use some validated questionnaire like the state trait anxiety questionnaire. And I think that's the scale we were actually using for these fake numbers. So there are validated questionnaires that measure anxiety. There are even validated questionnaires that measure anxiety towards a specific task. So that would be state anxiety. Trait anxiety is for me, state is for thing, for a specific task. So we would say this is a questionnaire that measures state anxiety relating to posting on social media. So when we got these numbers, these 20 to 100 type numbers, those were people's scores on the state anxiety questionnaire that we gave them. And then this was the number of tweets that they made in the past 6 months. That was just the example. This was fake data that we randomly generated. In the second half of today's class, in the R session, I'll show you some more data from a different, from this same data set. We'll go through it. The MCQ, will we be expected to show any knowledge of the underlying mass of these statistical tests? Tricky question. Might I ask you what a R squared value is measuring? I might ask you like this sort of equation that the R squared value is a proportion of how much of the variance is explained by the model to how much variance is their total. I probably won't ask you this equation because that's a lot of math, right? That's a little bit beyond the scope of a communication school module, I'd say. So I probably won't ask you how do you compute the model sum of squares, but I might ask you how do model sum of squares and total sum of squares relate, or how do you calculate R squared if you have model sum of squares and total sum of squares. I won't ask you the deep underlying math, but I might ask you something more kind of surface level conceptual about like basically what is an R squared value telling us? And an answer to that might be the proportion of variance explained by the model to total variance in the data set. So I won't ask you the hard math, but I very well might ask you conceptual math. I certainly won't give you a bunch of numbers and make you compute anything. That would be cruel and unusual. This is not a math class. Anyway, definitely get your regression questions ready. You can feel free to hit me with any of them during the break and after the break. I know we covered a lot, and regression is a lot to take in on your first time experiencing it. I hope you've had a chance to download the new R script and data set. The data set is called twitter.csv, and the R script is called week5.r. Hopefully they are in your R working directory, so we can run through those together and see how to run a regression in R Studio. So it is 2:59 right now. I'll see you at 3:09. Great. Hello, everybody. Welcome back. Looks like it's just about time. I did get one question. Someone asked if maybe I should hold this off until I'm sure everyone's back, but I'm going to say it now. It'll be on the recording anyway. Someone asked if the assessment, if the multiple choice test at the end of the term will have questions from the textbook, or will have things from the textbook. Yes, definitely. Andy Field knows more about statistics than I ever will. So his resource should be considered primary and my lectures secondary in your journey to understanding statistics. I would say definitely make sure you have read each assigned reading. It's really beneficial to read along with the lecture. So either like right before or right after the lecture, read that week's chapter. That way it's like fresh in your head. You kind of still remember what a regression looked like in my example or in Andy Field's example. Yeah, making sure you're on top of the reading will definitely benefit your understanding of statistics and benefit your potential scores on assessments. Somebody asked, what is the significance of the reading attached to the first assignment? Suggested reading. I think I might have labeled it as such. So if you note in the assignment checklist in Brightspace, part of the goal of a discussion, or you might have noted this in your reading around other scientific articles or in your reading of the APA template guide that I gave. But a big part of writing a discussion is it's in the name. It's discussing. It's putting that your findings into context. It's bringing them into discussion, into comparison and contrast with other findings in a field. The reason I give a couple suggested readings is because I don't expect you to have a background knowledge of the specific topics on the assessment. So this time it was mental workload and system usability. You don't need to know anything about those going into this class to do well on this assignment. I give you a couple suggested readings as a starting point for finding papers that you might want to mention in your discussion to compare and contrast other work to. Or I gave both of the scales, the papers that the scales come from, in case you want to note any strengths or limitations of those scales in your discussion. But also the papers that are related might be good for finding other related works that you can bring your work into discussion with. Talk more about this next week during the assignment Q&A. But the reason I only give a few related works, but expect you to have more, is because you can go in any number of directions. You could find all sorts of different things to relate this to. Really excellent versions of this assignment, I find people end up trying to relate the question at hand to some societal question or some broader question that they're interested in. So people who have taken this class from like the economics department have ended up trying to relate things that we talk about in the assessment to some economic reality, where people in the education school have tried to relate it to education. And I think those do an excellent job. And it's kind of an illustration that your discussion, when you broaden things out and bring it into, when you bring your specific results into a greater discussion with the broader context, with the broader area around it, there's a lot of different ways to get broad. There's a lot of different ways you can relate your findings to other findings. So I don't give too many findings because I don't want to constrain which direction you go in. There's an unlimited number of directions to go in, and part of the assignment is to be creative and to find those directions. I said, will there be concepts on the exams that are not covered in the lectures and only covered in the readings? Yes, Andy Field has a funny writing style. I think that is a very judicious way of putting it. I also think he has a funny writing style. But yeah, I would say the bulk of the exam questions will be things that come directly from lectures. There'll be statistical tests and concepts that come from lectures. He might get more into certain details about like what is a sampling distribution, what is a normal what is a normal distribution, what are some of the assumptions of a given statistical test. But all of the things that he's getting into greater detail, I will have at least mentioned in the lecture. It's not, by the way, it's not appropriate to comment on the teaching team's appearances during the lectures. I don't think that's a very good thing to be putting into chat. But yeah, no, yeah, it's all right. Well, it's not up to me if it's all right, it's up to you now. The book gets into greater detail than I will in my lectures, but I wouldn't say there's anything that Field will cover that we wouldn't have even mentioned in class that you would have had to be like reading, line by line, word by word to get. But I'll definitely say that if you feel very comfortable with each different lecture, you'll probably feel comfortable with the exam. That part of feeling more comfortable with my lectures might be reading the chapter that kind of goes into that better detail, but I wouldn't say there's going to be like these tricks that like, haha, Field mentioned this one thing and you better have read that. It's a useful resource to preparing for the exam, but it's not, there won't be anything that only comes from the book, I would say. I'm being hesitant. I don't want to say that. And then there's like one thing that like, I didn't get into enough detail that Field fully explained. I would suggest you read the book, but don't necessarily read it for like every discrepancy between his points and my points, because the test will mainly come from areas we both talked about. Anyway, time to do some R. Hello, again, as usual, we will start by setting our working directory. Yeah, so it might say on your version of this file, depending on when you download it, we will start tweet, because I did find and replace RT with tweet or Twitter or something. And I didn't catch that one, but we will start, is what I meant to say, by setting our working directory. Hopefully that should be pretty familiar. You read in your data set. Hopefully that will be pretty familiar. Hopefully the first two commands go smoothly and you have your Twitter data set now in your global environment. And as always, whenever we get a new data set, we just want to run head and tail. And again, we do that just to see what our data set's made up of. What variables do we have here and how many observations do we have? So you can already kind of tell we have 3 variables and 100 observations. We knew that just by looking in the global environment, but now we know what the variables are. We again have X, which seems to be participant number. We have tweets and we have anxiety score. And we're going to run just the same hypothesis that we had in the lecture today. So the hypothesis is that you can use anxiety scores to predict number of tweets. And I phrase this as this is the tweet someone made over the last 6 months. But I think the way Andy Field phrases this in the textbook might be even better, that you might say that you're using anxiety score to predict some future value. So maybe you're using anxiety scores to predict how many tweets people will have over the next 6 months. So that's something where you can measure anxiety right now, but you won't be able to measure that outcome variable for another 6 months. And that's one reason you might want to use something like linear regression. So first you fit your model with data that you already have. So you figure out what should that equation be to make that prediction and how good is that prediction. Then if you know that that does make a prediction that's kind of good or good enough for you, then you can use it to make forward-looking predictions. You can use it to predict values for variables that you don't have yet. And Field gives the example of, his dad buying him a guitar and something about his music class evaluations predicting how great of a guitarist he would one day become. I don't know. He makes silly examples anyway. So anyway, there's head and tail. We know what we have. We have 100 participants, 100 observations of these 3 variables. And we already know that this is 1 participant per row. We know this is not an experiment, so it's not like there's people recording like multiple observations. It's not that people were in multiple conditions. So we don't really need this ID number row, this X. So like last week, we can set X equal to null, and that just gets rid of the X variable, that X column. So now head and tail just have tweets and anxiety, numbered 1 to 100. And as always, we want to get some descriptive statistics. Firstly, because it's important whenever we are reporting our statistics to describe each of our variables of interest. So if our hypothesis has tweets and anxiety score as variables that we're interested in, we should give some descriptive statistics for tweets and for anxiety score. So we should report a mean, a standard deviation, and we want to see our min and our max and our median and all these, partially to look for outliers or to look for impossible points, and partially just to be able to report them. And we'll probably just report them in a table. So the same way in today's lecture that I had a table with some of the details about my regression, I'll probably put my descriptive statistics in a table so I don't have to have like line after line of text in my writing that's like the mean was this, the standard deviation was this, the minimum was this. You probably would say your mean and standard deviation in text and then put other descriptive statistics in a table, but that's kind of up to you. That's a stylistic thing. So I look at my mean, my standard deviation for both tweets and anxiety. I'm just off the top of my head, I see that my minimum and my maximum for tweets was between 10 and 526. So they all seem like perfectly possible values. My mean and my median look pretty close to each other, so I'm not expecting any terrible outliers. Same for anxiety, that my mean and my median are really close together. My min and my max are both possible scores, are 30 and 78. So now I'm feeling comfortable that there's probably not any points that I need to delete because they're like terrible. Like I didn't accidentally put in 500 or something. Standard deviation is, so it's just this SD command and then the variable. So SD of Twitter $anxiety is that. The formula for actually calculating standard deviation is in my slides about variance. So it's, you get the sum of squares for the mean and then you square root it, but SD of variance does it for you. Yep, great. So now we want to make a histogram for both of our variables. And why do we want to do that? So part of our assumption for any of our inferential statistics that are parametric, so anytime we're going to be using inferential statistics in this class, one of our assumptions is that our statistics come from, that our variables are parametric, that they are normally distributed and that they're continuous. Now, we don't really need to check that continuous assumption. I already told you what the variables are. You know that they're numbers, they're not categories or ranks. But we do want to check that they're normally distributed to make sure we can run a regression. So to do that, we're going to do the same thing that we've done for the past couple of weeks. And this will be fine if you do this on your assignment. This is just making two histograms or making histograms for each variable, just to make sure that they're normally distributed visually. And again, a normal distribution is one that's shaped like a bell curve, that the median is where most of the values come from, and then it slopes down on both sides roughly symmetrically. It doesn't have to be perfect. For our purposes for visual inspection like this, we would say that this is a normal distribution because the middle is the high point, and then the next two highest points are on either side of the middle, and the next highest points after that are on either side of that. So it doesn't really have to be perfectly symmetrical as long as it roughly follows that bell. And like I keep saying, I keep alluding to this, it's a pain to do these extra tests, but in the future, we will teach you a test for just determining whether you have a normal distribution. For now, we're going to just keep doing it visually by looking at the histogram. And that looks normal to me. Again, for whenever I make a histogram, I set these breaks myself since I knew the min of the possible minimum was 0 and the max was above 500. I just went by 100 up by 100 at a time all the way to 600. That way, everyone would be represented here. You could have broken these breaks down however you wanted. You could have had buckets of 50 or of 200 or whatever. I found 100 to be a pretty good way to visualize this. Next, for anxiety, same sort of idea, is I set breaks between 0 and 100. But this really depends on what the real questionnaire we used was. So if we had a questionnaire that goes from, let's say we have a questionnaire that goes from 6 to 126. In that case, I might set breaks from like 0 to 140 or something. That way I know all of my possible values are represented. And you can set by 10s, by 20s. Yeah, you set your breaks yourself. You probably, I'll give you this hint next week also for the assignment review. But histograms are your tool as a data analyst, but they don't answer your hypothesis, right? If you showed this graph to somebody and you told them what your hypothesis was, this has nothing to do with your hypothesis. It kind of underlies an assumption to testing your hypothesis, but that's too removed to be showing your reader. This is a tool for you as a data analyst to verify that it's normally distributed. Then you can tell your reader, I verified that both of these variables were normally distributed, but you wouldn't necessarily show them your histogram. So you can put whatever breaks you want. Your hypothetical reader of a report, of a paper, won't see your histogram. Your hypothetical reader of the code, so if I'm checking your code, I'll see what breaks you used, and I'll assess whether or not you could whether or not you could tell what the distribution looked like given the breaks that you used. But you can set different breaks if you want to. Yeah, so the histogram would look different depending on your breaks. So let's see what it would look like if I went by 20s instead of 10s. So I'm just getting rid of every odd number here. So what if I went from 0 to 100 by 20? Then my histogram looks like this. This is a lot less informative, but I'm like, it kind of looks normal, but I don't know. Like there's a lot of points in there. So the more I break it down, going by 10s would be a little bit more granular and let me see that nice bell shape. If I went by 5s, I might see even more information. But the breaks is the amount of breaks and the size is really up to you as a data analyst to just figure out if that's normal. If there's an empty bar in the histogram, if there was an empty bar over here, so maybe we had like 1 point here and then none and then a bunch, that's probably fine. That's probably normally distributed because it's just a small amount on the ends and a lot in the middle. If you have an empty bar right in the middle, if you have like some high ones, then an empty one, then some more high ones, that's a problem. That means you probably don't have a normal distribution. I'm glad you asked because I think I can answer this. I can say, yeah, I think I can answer this clearly without having to be vague. You should not include histograms in a written report, but you should include them in a code. You should include in a written report some indication that you verified that you had normally distributed data. So you might in future reports in assignment 2, for example, if you had a statistical test that could tell you really kind of succinctly, here's some verification that this was normal, then you could put that in. Yeah, okay. Oh, you already know. Yeah, if you want to run a Shapiro-Wilks test and tell me the result of it, you can tell me that the result for your Shapiro-Wilks test was not significant. But if you're just using a histogram to visually inspect normality, you can just tell me you verified that both variables were normal. But as a reader, the histograms in there are kind of distracting from the main point of the written report. A Shapiro-Wilks test is at least one little quick line, but we haven't covered that yet in class, so I don't expect them on the first report. If you already know how to run that and include it, you can, but if you don't want to, you don't have to. All you need to show me is I want to see code that you did run a histogram and you check that it was normal, and then you tell me in the written report that you checked that it was normal and that it was normal and that matches what I see. Like if I run your code, can I verify that this was normally distributed? But that's all you really need to do for the assignments anyway. And that's why we run a histogram before any of these tests, right? We're just verifying this assumption that we have normally distributed data because we're using parametric statistics. We're using statistical tests that assume we have normally distributed data. So we've done that. We also want to run our box plot. This is how we would first see if there's maybe a skew to our data, if there's the points on the high end are a lot higher than the points on the low end or something like that. And we might be able to see if there's potential outliers. So when I run my box plot for tweets, I see this one potential outlier. And remember when we talked about variance, we talked about how the box plot determines what this max is. So that's the median plus 1.5 times the interquartile range is here. So anything above that is what the box plot is saying, this might be an outlier. But that's not a really great description of what an outlier is. And if you've been keeping up with the book, I think it's chapter 5, something, or no, it's chapter 4. It's Jane's Superbrain 4.1. I have a sickness that I know specific sections of the book at this point. Jane's Superbrain 4.1 and 4.2 talk about how we as data analysts determine what an outlier is. And it's a little bit different than what the box plot's determining as an outlier. As a data analyst, you would say that for your sample size, an outlier is a point that you wouldn't expect to be distributed, that you wouldn't expect on the distribution. So if something's more than 3 standard deviations away from the mean and your sample size is around 100, you wouldn't expect points that extreme, that you would expect 99% of your points to all fall within 3 standard deviations of the mean. So if you find a point that's more than 3 standard deviations above or below the mean, then that probably is an outlier. And that's how we're actually going to determine whether we need to treat this point or not. So don't just take boxplot's word as gospel, but take boxplot's word as a piece of advice. We're going to check this plot, but we're going to check this point, but we're not going to deal with it just yet. We're going to check if we need to deal with it. Yes, great question. Is it the same for boxplot as well? Just need to mention it in your results, not in your discussion. In your results section, you would want to say something like a boxplot visual inspection confirmed that this variable was not skewed. So you probably wouldn't explain your you probably wouldn't include your box plot in your results, but you would say something like the variable was not skewed and this was verified by using box plots. So again, yeah, because this visualization doesn't actually address your hypothesis, you don't need to include it. But because part of your assumption for doing this test was that you didn't have skewed data, that you had normally distributed data, you might mention that you used a box plot to verify that. Someone asked, why do you expect all points to be within standard deviations? Great question. If you've read chapter 4 of Andy Field's textbook, and especially Jane's Superbrain 4.1 and 4.2, apparently, we know that a normal distribution has the normal distribution is defined by how many points are within each standard deviation. So within the first standard deviation in either direction of the mean, that's where 67%, 2/3 of your data lies. Within 2 standard deviations of your mean, that's where 95% of your data lies on a normally distributed variable. And then within 3 standard deviations is 99% of your data. So that's why we would expect that all of your points are within 3 standard deviations. because we're taking a sample from what we're assuming is a normally distributed parameter, from a normally distributed variable. So if we have a bunch of points that were outside of outside of that 3 standard deviations, we're saying we got all these points that we don't expect represents more than 1% of our total population. Our sample size is only 100, so we probably shouldn't have a bunch of these points. We probably should have like one or none of these points that are outside of that range. If you have a really big sample size, you might say, I have 1,000 participants. I might have expected about 10 of these outliers, so I'll just leave them be. But for our purposes, we have 100 participants. We might be okay with one outlier. For the purpose of this class, we're going to say, nah, even if we have one outlier, we'll treat them because it's very unlikely we would have even one person more than 3 standard deviations away from the mean. But anyway, we haven't determined if we have that yet. So that's our box plot for tweets. Let's also run our box plot for anxiety. And again, this is just telling us how skewed our distribution is, whether we have more points that are on the high side, more points that are on the low side, more extreme points on one side or the other. And it looks like the anxiety is really, really normally distributed, that we don't have any skew to it. We don't have any potential outliers. So anxiety is all good. But we do want to check if that 1 point from our Twitter box plot, this one max value for tweets, if that is an outlier, if that is more than 3 standard deviations greater than the mean. So I got a question about what kind of code we need to know. None of the code that Andy Field uses needs to be included in any of your assignments or needs to be known for any of your assessments. He uses like R commander and he uses ggplot. That's a little more advanced than what we teach for this class. Any R code only comes from what I teach you in this hour and in these worksheet thingies, these scripts that I make. So if something's more advanced than that, if you want to use it, go ahead. If you feel comfortable using something from the textbook or something you knew ahead of time. But you definitely don't need to feel compelled to use any of the more advanced things that Andy Field does code-wise. So anyway, let's check this data point. So we know that that is our max for tweets. It's 1 point on its own. So we already kind of know, if we just go back up here and run max of tweets, that point is 526. So all we need to check is 526 more than 3 standard deviations greater than the mean? So we can just run that as one line of code. 3 standard deviations greater than the mean is 551. So 526, not big enough to be considered an outlier. Let's just leave it alone. Let's throw it in there. I feel like I'm writing a really descriptive script. Should it be as simple as possible or should we explain each step? No, you probably won't have quite as many comments and quite as robust comments as I write. You'll never see code in the wild that's described like this. You can describe it really kind of narratively like I do for this example, but in reality, when I write actual code, my description would be something like run descriptives for Twitter, run descriptives for anxiety. Like it would be pretty bare bones. It would tell you what the next line or a couple of lines is meant to do, but it's not going to tell you it in prose and like a story. I wonder if I have sitting around a script that I've used recently that I could show you what my R scripts normally look like. Let's see, tetrisanalysis.r. Yeah, import spreadsheets, get the relevant Ps, add the timestamp of video start, import packages. Like it's pretty bare bones, my actual comments, and that's all I would expect in the assignment. There is an R code to check for outliers, easier than writing out the equation. If you check Jane's Superbrain 4.2, Andy actually tells you what the outlier summary code is. I don't know if he writes that one himself or if that one's for public consumption. You can check that quickly or you can run each of these. I do it like this just to make you kind of do it by hand and force you to think about what you're checking. But if you're using R regularly, you'll probably want to write this up as a script, and you might check out Andy Field's ideas for how to do that. So I'm checking now which points, if any, are bigger on Twitter than 3 standard deviations greater, 3 standard deviations bigger than the mean. So there are none, integer 0. There are no points bigger than 3 standard deviations of the mean for Twitter. Check that for how many points are below 3 standard deviations below the mean, no points. And do the same for anxiety. And again, I keep getting this integer 0. That just means there are no points that are an outlier for either direction for either of these variables. yeah, you can do this a little bit easier with some scripting with z-scores or with a custom function that you can write. There's probably some functions that you can just run automatically that are already written for you, but I just do it by hand for the purposes of this class, and I do it by hand when I do my own code. Actually, I think I have. I'm not going to show you my own code again. It's pretty ugly, but I do it by hand still, even though it takes a little bit more time, just so I'm sure that I'm checking each direction and I'm looking at my box plot and like inspecting individual points, just to be really like meticulous. So no outliers detected. That means we can go ahead and look at our scatter plot. So we know that we want to model a linear relationship between these variables. So we're still, no matter what we see here, we're still going to try to run our regression model. But this scatter plot might help us visualize whether we're going to expect a regression line to actually be descriptive, whether it will be pretty different than just the flat mean line, or whether it's going to be just flat, that there's no pattern. And looking at it, I'm like, all right, this is actually a pretty linear relationship. I can expect a line with a slope that looks like what I'm drawing with my cursor here. So we can go ahead and, oh, shoot. Excuse me, that test. Okay, well, we can go ahead and check a correlation between them, but I should not have done that. That is bad. I hope you're paying attention to my what I'm talking about right now, and I hope you're paying attention to my video rather than to just the script, because we should not run a correlation. That is not part of our hypothesis. It's actually really bad practice to run more than one test, or to run more than the test that you need. That's overanalyzing your data. That's p hacking. That's phishing with a p. You're going out and casting your line because, you know, your p-value, you're trying to find something less than 5% chance likelihood of observing given the null hypothesis. But if you cast a bunch of lines, if you run a bunch of different tests, you'll find something significant. So because I'm testing a prediction, I should not be running a correlation at all. How did that sneak in there? Now I'm like, maybe I should play it off like I did it on purpose. No, I did not do that on purpose. The correlation part, I was copying and pasting from last week's code, as you probably already assumed. But I should not have done that, because you should not be running a correlation if what you're actually measuring here is a regression. So I deleted that code, pretend it never existed. Someone asked, do we include a scatter plot in the report? If the visualization helps you demonstrate your hypothesis, then it's good to include in the report. So we'll get to the linear model in the summary, just not the correlation. So if you run a correlation, should you run a regression on your scatter plot to more clearly highlight the direction? That is a good question. If you are doing a correlation and you want a line of best fit that helps you describe your data, then running a regression is a good idea just for that purpose. Don't report your regression. Don't try to summarize the model or anything, because that is superfluous to your hypothesis. But that line of best fit might be useful for your hypothesis. And the only way to get that line of best fit is to run a regression, unfortunately. So that's a good question, Jake. I would say yes. If you're running a regression and you want to include that line of best fit, it's okay to run the regression just for that purpose. And then don't tell anyone about the, like, don't report the regression. Don't tell me about the p-value, because you did not have a hypothesis, so you don't have a p-value. That p-value is fake. It's an illusion, but the line is actually real, and it does describe your correlation. But yeah, if you were running either a correlation or a regression, including that scatter plot's a good idea, because either way, you're talking about how these variables either relate or predict. Are we running a correlation or a regression for the assignment? How do we know which one to run? I don't want to answer that, and I don't want the teaching team to answer that, because I think that would be like us giving away the answer. But I'm opening the floor to anyone in the class to answer. How do we know whether we're supposed to use a correlation or a regression? And I tried to make a big deal in today's lecture of the sirens going off. Yes, exactly. The keywords, the language of your hypothesis is how you know which test to use. Thank you. You guys all nailed it. I couldn't have scripted that better. I didn't say anything, but the language of your hypothesis is exactly how you determine which test you should be using, and you should not be over testing. So anyway, let's finally run this darn regression. We tested our assumptions. We visualized our linear relationship. Let's run the regression. And just like last week, whenever we run these these inferential statistics, it's actually so underwhelming. Like it's like the shortest little line of code to do all the work. In this case, the equation is LM, linear model, LM, and then in parentheses, your outcome variable, and then a tilde, and then your predictor variable. So in the past, you would put like, you just put things in order in commas. This time, you want to do that tilde, and that's because later on, if we had other predictor variables, we could have something like, let's say we had age as a predictor variable, so we could add age in there. And let's say we had gender as a predictor variable, we could add gender in there. The reason the linear model is written like that is you only have one outcome variable. So you put that first, and then you put the tilde, and then any of your predictors, which might be a long list. In this case, we just have the one predictor, it's anxiety. So we can run our linear model, and we want to give it a name. We want to save it to our global environment. So we call it tweet model. You could call it anything. The name's not magic. You could call it model. You could call it reg for regression, whatever you want to call it. But I called it tweet model because I want it to be descriptive in case I have a lot of different models. This is the model for predicting tweets. Or maybe I would want to call it anxiety tweet model or something like that. So that goes into my global environment, and it's kind of mysterious. It just says list of 12. And that's because when you run a regression, I was telling you R does this in the background and that in the background. It checks your predictors, it checks your F test for your R squared value, it checks all this other stuff. That list of 12 is like all the different things R does for you when it runs a regression. Luckily, there is a handy little function called summary that lets you just get the important stuff. So if I run summary of tweet model, you get to see exactly what I showed you in class today. And that was your multiple R squared value. Oh, maybe it's a little different. Maybe we changed a data point here or there because that's 0.3137. So whoever said that they squared their correlation and got 0.3137, there you go. Maybe somewhere along the lines I changed something. There you go. Yeah, Yi was on it. But yeah, you got me. So this is the output of the summary function of your linear model. So that linear model is your regression equation, is your regression. And then the summary of that gives you all that important information that we talked about. So it gives you your intercept, your y-intercept, gives you your slope. So this was negative 0.56197. It gives you p-value, a p-value for that predictor. It gives you a p-value for your model overall, which in a simple linear regression is the same value. Here's your R squared value, which was just the square of your correlation. So whatever your correlation was last week, square that, you get your multiple R squared. That's how much of the variance, how much of the change in tweets can be explained by change in anxiety. In this case, it's just the square of your correlation because that's exactly the same as measuring covariance. But in this case, we're asking, how much of the total variance in tweets can be explained through our model? And now we're saying 31% of that variance can be explained by our model, or we would actually adjust it and say 30% of the variance in tweets can be explained by anxiety. That still leaves 70% of variance that's not being explained by our model, but 30% is done. Maybe we can add some more predictors and predict a bit more. And it's probably pretty likely that other things, other individual differences between people that we probably couldn't model at the population level are explaining some of that variance as well, that it might be, there might just be individual differences between people that make it impossible to explain all of our variance. So this tells us tons of information, like I said, but the most important parts that it's telling us are our values of those betas. So there's our beta naught, our intercept, and our beta 1, our slope. And hopefully I copied them in there correctly, but we can say that our straight line equation is number of tweets equals slope minus intercept minus 5.62 times anxiety score. Or you could have put it the other way. You could have said number of tweets equals negative 0.562 times anxiety score plus 5.5365. So that is to say you can actually put in their anxiety score, put in a 60 or whatever, multiply it by that number, add that number, and that gives you a prediction for number of tweets. That tells you where the red line will be or where the regression line will be for an anxiety score of 60, which is your prediction for your number of tweets for that anxiety score. You can also report your R squared value. So your R squared value was this adjusted R squared, let's just say 0.31 because we want to report statistics to 2 decimal places. Then we would report our F test. So that was 1 and 98 degrees of freedom. So F of 1, 98 equals 44.8. So that was the F score. And the reason we want to report our degrees of freedom, I kind of alluded to this, but the way you get your p-value is that for every different sample size, for every different amount of degrees of freedom, so for every different number of models and for every different number of people in each model, the F distribution is a little differently shaped, that it's more likely to find an extreme difference between 2 models if there's only like 3 points predicting each model. On the other hand, if you had like thousands of participants and you found a really extreme difference, then you would be really sure that that is that's rejecting your null hypothesis, that was minuscule chance of seeing something that extreme with that big of a sample size. But that's why we report our degrees of freedom, because that it's the degrees of freedom and the distribution that come together to give us our p-value. So we report our model equation, our p-value. We would report the value of this beta and this confidence interval maybe in a table, or this p-value for the predictor in a table, like I did in the lecture. And that's pretty much it. The only step left is if we wanted to add that line of best fit to our plot to visualize it, we could do AB line. So AB line means give it a draw a line with an A and a B. The A is the intercept, the B is the slope. And that's really easy because we can just tell just use the slope and the intercept from this model, and it knows just where to look. So it will look for the slope and the intercept of that model, and you can pick whatever color you want. I picked color equals red. You can pick color equals blue, whatever you want there. It all works out. You can put other parameters in there too if you want like a dotted line or a striped line or whatever. If you want to know more about the parameters you can use with AB line, you can just go up to this help tab, type AB line, and you can see that you can put things like, there's a lot of things you can put in there. You can do color equals light gray, LTY equals 3. So I think that's line thickness. So we could do like LTY equals 3 and see what that looks like. We probably already add a 3. Let's see LTY equals 5. I don't know. They all kind of look the same. But you can add different parameters, style your line however you want. There's different line colors and types. You can read in the documentation for R about all of the different graphical parameters you can add in there. Line LWD is line width. I think we were doing line type. So yeah, there's your really thick line. That looks terrible. We want to clear that before we put a new one in. So clear our plot, because it just draws on top of your last plot. So, it draws on top of your last plot. So you can't draw that line unless you have a plot in there already. So let me put my scatter plot back in. So I want to use that scatter plot. And let's say line width equals 2. Or I can draw my scatter plot. And I can say, let's try that line type thing now and see if that looks any different with without a line already drawn. Yeah, line type 5 is a dashed line. So there's different graphical parameters. You can make the line look different. But in any case, this is about what you would want to include in as a graphical demonstration of your hypothesis, that you can say, not only is this a predictive model, but because it's a predictive model, I'll even show you the line. This is the line that describes how those predictions are made. These are my predictions, and these are the actual values given this predictor variable. And when if you're doing a regression, you would always want to put your predictor variable along the x-axis and your outcome variable along the y-axis. It's kind of just convention, but that's the way you expect that to be seen. If you're instead running a correlation, you could put either variable in either spot. It doesn't really matter. Just make sure you put them in the appropriate order for the regression. That is, whatever you want on the y, then whatever you want on the x, if you want to draw that line, or else your line will be like tilted the wrong way for your variables. So make sure your line is tilted the way you want it to be tilted. But yeah, this is something you could and should include in a report on a correlation or a regression. You can skip drawing the line if you want to. If you're doing a correlation, you should definitely draw one if you're doing a regression. And you should only include that line if you have a statistically significant relationship. If what you found was not statistically significant, it's kind of misleading the reader to include that graphic and that line, because you're implying that there's a relationship or a predictive model here when there's not one. So if you have a statistically significant model or a statistically significant correlation, include this. If you don't. And also note that if you're including a plot like this, it's good to include an X label and a Y label that are descriptive. So anxiety score, number of tweets. I don't include a main title for a graph like this. Like if I put main equals tweet graph or whatever. If I put that, then I would have a main title, but it's actually not great to put a main title in an APA formatted report, because figures in APA reports don't have a main title. They have a caption underneath. So don't include the main title, include the caption. So instead, just like that, that would be a perfectly good graph to include that explains this hypothesis or that speaks to this hypothesis. Even better if I also include a line of best fit. Yeah, that's how you do a regression in R. Easy stuff. Putting the simple in simple linear regression. Am I right? I hope so. But feel free to send me all your emails and questions and complaints over the next couple of weeks. I know, it's pretty tricky actually. Feel free to send me all of your comments, complaints, anything you need over the next week, because next week's class, next Thursday, the 20th, will be the Q&A. That will be where I'll answer any kind of questions about the exam that I can. Or about the assignment that I can. I'm not going to do the assignment for you. I'll run through a sample assignment, and we can cover any statistical concepts in R that you might have been struggling with. So send me any of those questions so I have plenty of time to prepare material for it and to try to answer you via email also. And I'll see you next week. Thanks, everybody.